Hello and welcome. There are two terms being used in this title which are important to understand. And the first one is programming declaratively, and the second term is the logic paradigm. So let's be clear about these two terms. When you think about programming declaratively, you might think of languages such as SQL, HTML, or regular expressions as examples of declarative programming, and you might notice that the basic theme behind these languages is the fact that you are describing what you want, not how you want it done. For instance, with SQL, you're describing the nature of the data that you're interested in retrieving, not the algorithms used to fetch the data. Similarly, with HTML, you're describing what you want the web page to look like, not what algorithms to be used or how the layout has to be painted on the web browser. Coming to the logic paradigm. Now, each of these examples of declarative programming like SQL, HTML, and so forth, these are all domain-specific declarative programming facilities. And the logic paradigm, in contrast, is a general-purpose declarative programming facility. And this is what this presentation is about. It's about how to use this paradigm to do general-purpose computation in C++. This is the rough outline of this talk. I'll start off with introduction to the basic concepts behind this paradigm. Just like, when you pick up the object-oriented paradigm, you start by learning what is a class and what's objects and so forth. Similarly, we'll be understanding the fundamental concepts behind this paradigm. And then we'll represent these concepts in code in C++. And for this, we'll be using an open source library called Castor. Note that you will not need any extensions to standard C++. This all works with standard C++. Most of this talk is around examples, live code. And we'll basically start off with very trivial ones and move to increasingly complex ones. So we'll kind of build on the complexity as we build our understanding of the paradigm. There are two key things I'm trying to demonstrate in this talk, and the first one is how to use the logic paradigm for general purpose programming. So basically trying to understand that this is a general purpose facility. The second thing is multi-paradigm programming. How can you mix this paradigm with the other paradigms that are already available to C++, and we'll see how this paradigm blends with the other paradigms at a low level, and you're free to mix and match these paradigms. Before we get into the concepts of the paradigm itself, let's just understand the space of declarative versus imperative programming languages. If you notice, most of our programming languages are imperative. When I say imperative, what it means is you are explicitly specifying every single step of the computation that needs to be performed in order to achieve the results. And the machine simply follows those instructions. So why are most programming languages imperative? If you think about this, you might come up with several solutions, but one of the key reasons for this is the fact that the hardware, the microprocessor, is itself imperative. So therefore, it's very natural to have higher level languages to also be imperative. All paradigms have their strengths and weaknesses. What's the weakness of the declarative programming paradigm? The key weakness of this paradigm is that you do not get control on the steps used in the execution. It's kind of by definition. This may be a problem in certain cases and may not be a problem in certain cases, but when you want that control, you don't get much of it. So that's the key weakness of this paradigm. Which brings us to the weakness of the imperative paradigm. Here you will notice the weakness is quite the opposite of the declarative paradigm in the sense that you are always forced to specify every single step to be used. You don't have a choice. You might start observing our motivation, our desire to mix these two paradigms so that we can specify the explicit instructions when we are interested in taking control of the execution and leave them out when we don't care about them. So we can switch to the declarative model of programming at that time. So that's the real motivation for multi-paradigm programming here. Coming to the logic paradigm itself, this paradigm comes with its own computational model called the predicate calculus. This is kind of analogous to the Turing machine being the computational model for the imperative languages like C, C++, Java, and so forth. Predicate calculus is Turing complete. What it means is if you can compute a value with the Turing machine, you can compute the value with predicate calculus. So computational power is equivalent. We've already talked about the logic paradigm being declarative, which basically means you're focusing on what you want, not how you want it done. This idea of general purpose declarative programming has also been referred to as the holy grail of programming. The idea being that user states the problem and the computer solves it. And in computer science, logic paradigm is one approach towards this holy grail. Now let's actually go into the concepts. This is the first introduction into the concepts behind the paradigm. And the first concept is that of a relation. Since you are programming declaratively, you are not specifying the steps used in the computation. Instead, you are providing information regarding the problem domain to the machine so that it can decide on how to perform the computation. Basically, you are providing information to the machine to work with. This is conceptually similar to how you would ask a person to get some job done. You would provide him with some amount of information and then he can go and decide on how exactly to use that information to achieve the end result. The way we provide information to the machine in this logic paradigm is using the concept of a relation. So relations are our way to express information or describe information which is then consumed by the machine. And since you're not specifying the steps used for computing the end result, the machine needs some algorithm to go ahead and compute the value. So what it does is it uses a general purpose problem solving technique to solve the problems. And this general purpose algorithm is a combination of two steps: backtracking and unification. We'll be examining all these three concepts, that of a relation, backtracking, and unification, in the coming slides in more detail. Let's first look at the concept of a relation. Before we talk about relation, we need to know what a set is. The definition is straightforward. It's basically a collection of unique objects. I have put unique in brackets here because this constraint is often relaxed in practice. For instance, in the case of relational databases where a table can have duplicate records. This is also the case with the logic paradigm. I have two sets on the slide. One is the people set and the other one is the gender set. If I were to associate the people with their corresponding gender, what I would have is a bunch of lines as follows. So basically we are stating that Frank is male, Sam is male, Mary is female, and Denise is also female. Now this collection of lines is what is a relation. And since this relation is between two sets, this is basically a binary relation. The key step we're going to take here is to represent those lines also as a set. So what I have here is the relation being represented as a set called gender of. This is a set of pairs because we are dealing with a binary relation. So the takeaway here is that a relation can basically be treated as a set. However, thinking of these relations as mappings between sets is quite useful, especially when you're designing your relations in this paradigm. Just keep this in the back of your mind. It's quite useful when you're writing code in this logic paradigm. The last bullet here is stressing the importance of a relation. This concept of relation is as fundamental to this paradigm as the function is to the imperative paradigm. In a sense, it's your fundamental building block. Let's contrast functions and relations a little bit further to get a better understanding of relations. What I have here on the slide on the right side is the same relation gender of from the previous slide. And what I have on the left is 4 primitive functions that you can write around that set. So my first function, given a person P and a gender G, will return me true or false. Basically, you can check if person P's gender is G. The next function, given a person P, returns me back his gender. The third function is actually the inverse of the second one. Given a gender G, it gives me a list of all the people who have that gender. And finally, the last one gives me a list of all items in the relation. I have deliberately skipped all the implementation details because it's quite obvious how you could probably go about implementing these functions. And there's many different ways you could probably do this with if statements and for loops and data structures and so forth. Therefore, I'll just skip describing those details and simply show you how the same set can be described as a relation. What you see here is a function. So we are describing the relation also as a function. The return type of this function has been tagged with a type called relation. So when you see a function whose return type is relation, you know that it's a relation. Since this is a binary relation, this relation has 2 arguments, P and G. P for person and G for gender. Both are strings. But the string type has been tagged with a template called LREF. LREF is short for logic reference. Logic references are conceptually similar to references in C++, but their most basic difference being that logic references do not need to be initialized. And you can check whether a logic reference is currently initialized or not. My function is called gender. One of the important things of relations, since we are programming declaratively, is what's called as the declarative reading. In this case, the declarative reading is simple. It's as follows. P's gender is G. The declarative reading is a summary of what the relation stands for. I will now describe the implementation for this relation. And before I explain this, the workings of this relation, let me show you how to read this. So we start off with the declarative reading. Just follow my mouse here. We start from here. Say P's gender is G if P is equal to Frank and G is equal to male, or P is equal to Sam and G is equal to male, and so forth. So what you can see here is we basically have one clause for each record in the set. So we are only describing the information. We are not specifying any algorithms here. So what is EQ? EQ is the unification relation. EQ's job is to unify its two arguments. What it means is it will try to make the two arguments equal. So if you recall, P and G are both logic references, and logic references do not need to be initialized. In the case that P is not initialized, unification will assign the value frank to P, and the two arguments are now equal, therefore unification succeeds. Now in the other case that P has already been initialized with a value, in that case unification will compare the two values, and if the comparison succeeds, the unification also succeeds, otherwise the unification fails and returns false. So that's the basic idea of unification. It's simply a combination of comparison and assignment. If you recall from the previous slide, I mentioned that unification and backtracking are the two steps that are part of the universal programming, universal problem solving algorithm used by the logic paradigm. This is the unification part, EQ. There are a couple of things to take away from here. The first one is that the specification is declarative. You don't see any algorithms or data structures being used. We are simply representing information. There's no if statements or while loops and so forth. The other more interesting thing is that this relation subsumes the functionality of all four functions that we saw on the previous slide. And how that is possible, we'll take a look at it in the demo. We have the same relation here, the gender relation, and now I'm going to start using the relation in order to demonstrate how this one relation subsumes the functionality of all the four functions. Now before I start using this relation, let me point out a couple little things that I'm doing here to use the Castor library. First, I'm including the castor.h header file, and then using the Castor namespace. This basically makes the facilities in the Castor library available for use in this piece of code. Since Castor is a pure header library, there is nothing to either statically or dynamically link against. Let's try to check if a certain person P has a certain gender G. Let me try to see if Sam is male. So I'm going to phrase that question by invoking the relation with the arguments Sam and male, because that's what I'm trying to look for if Sam is male. What I have done here is simply phrased the question. I have not yet got an answer. I'm invoking the relation with the arguments, and that's phrasing the question. Now the way I look for the answer is as follows. I'm checking here if Sam is male, then print yes, else print no. So let's run this code and see what it prints out. It says yes, and that's the expected answer. Let's see if it prints anything different if I ask if Sam is female. The expected answer here should be no, and that's what we see. So we know this works. Now let's try to understand how this works. Let me revert this back to male. What I'm doing here is invoking the relation, and here I'm triggering the evaluation. This is a key step in understanding how this works. We have split invocation and evaluation. Invocation means passing the arguments. Evaluation means computing the result. Typically in C or C++ or Java, we basically combine evaluation and invocation into a single step, where when you call a function, it produces the computed value. Here we're going to split those two steps. This is an example of lazy evaluation or delayed evaluation, whatever you may want to call it. Now let's try to understand how exactly this works. What exactly is happening here if it is not performing evaluation? What it's actually doing is returning immediately back this expression as a function object and stores it in SM. However, it remembers the arguments that were passed to this relation. So basically P's value has been fixed to Sam and G's value has been fixed to male. So you can imagine this entire expression here where P has been substituted with Sam and G has been substituted with male, and that's the information stored here. So now we have this function object SM. Now we are able to trigger the evaluation on it by applying the function call operator on it. If it returns true, then we have a successful evaluation. If it returns false, then the answer is no. Let's understand how evaluation works. At this point, we are looking for a successful evaluation of this expression. And for this expression to succeed, all we need is one clause to succeed, any one of these. So if any of these 5 clauses succeed, we have a successful evaluation of the entire expression, and therefore it returns true back to the if statement. It basically examines the first clause. Here the value of P, if you recall, has been fixed to Sam and G has been fixed to male. So unification of P with Frank fails because Sam does not compare equally to Frank. So we skip the remainder of this expression due to short circuit evaluation semantics and move on to the next clause. Here the unification actually succeeds because P's value is Sam, and also the second half of this AND expression succeeds because G's value is male. So we have found a successful clause, which means we have successfully evaluated this expression and we return back true to the if statement. That's how the answer yes is printed. Now if we were to specify female here, none of the clauses actually match because we don't have a clause stating that Sam is female. If we had a clause of that nature, this would succeed. So if you had a clause saying Sam is male and another clause specifying that Sam is female, that's kind of bad data and therefore you would get bad output. So in either case, male or female, you would get the answer yes. Let's move on to a slightly more interesting question. Now instead of checking if a certain person has a certain gender, what we're going to do is ask what is the person's gender. So this is actually, we're trying to generate a result here, not simply check. Instead of specifying both values, I'm going to first declare a logic reference for the gender, which is not initialized with the value, and pass it in. So basically we are leaving the gender unspecified here. And this is the question we are asking here is, what is Sam's gender? When the evaluation succeeds, we are going to find our answer in G. If successful evaluation does not occur, meaning the evaluation fails, then we say not known. What that means is we don't have any data about Sam's gender. So if we didn't have a clause here stating Sam's gender, then the evaluation would not succeed. If Sam's gender has been specified, then we should get the value of G, and we basically dereference the logic reference in order to obtain the value. So it's like a smart pointer. Now let's see if we get the right answer. So it says male. So similarly, we can look for Denise's gender here. And we get the value female. So let's understand what's going on here. We evaluate one clause at a time. Now notice this time only the value of P is fixed, true? Let's say Sam. Whereas value of G is not. So in this entire expression, the first half of each of these clauses is going to perform comparison because P is initialized. And in each of these clauses, in the second half of these expressions, you're going to have assignment because G is not initialized. That's the semantics of unification, either comparison or assignment. So what we get from the evaluation of the first clause is this unification fails because P is frank. So we move on to the second clause. Now this time this part succeeds and we move on to the second half of this expression, and here the value of male is assigned to G. So that's how we get a value for G. Since this clause has been successfully evaluated, our entire expression holds true, and therefore we return to the if statement and the value of G is printed here. Now let's ask the opposite question. Let's ask for all the people, basically all males. Let's look for all people who are male. So now this time I'm interested in the people, not the gender part. The gender part is known. So I'm going to leave the person's name unspecified and specify the gender. All males. And I'm going to print P value. So let me get rid of the else because I know there's males in the system. So what I have here is phrase the question that P gender is male. Now let's see what happens when I invoke this relation. It says Frank. So what it's telling me is Frank is male. Although that is a correct answer, it is not a complete answer because I have many more people who are male. So what I'm actually interested in is finding out all of them, not just one, the first one. And in imperative programming model, our most natural way of going over all solutions or all values is to use a loop. And that's exactly how we look for all solutions for a relation. So let's see what we get as a value here. I get Frank, Sam, and Gary. So now we have all the answers, correct and complete. So what exactly happened here? The first time when this is triggered, the first clause is going to be considered. Now remember here P is not initialized and G is initialized. So therefore all the left halves, all of these left halves are going to perform assignment and the right half is going to perform comparison. So the first half here performs assignment of Frank to P, and then the second half basically compares. Now both of them succeed, right? Assignment succeeds and the comparison also succeeds. So we have a successful evaluation. So we return to the while loop with true. So the body of the while loop is executed and we have a value for P. We go back into the while loop now, and now something interesting happens. Instead of starting from the beginning, we will resume from where execution last left off. So we proceed from the second clause. This is the basic idea of backtracking. We know what paths we have taken and then pursue alternate ones. Okay, so this time our left half is going to perform assignment again, and the right half is going to perform comparison, as we discussed earlier. Here again, this time value of P is going to be Sam now, and that will simply compare and succeed, and therefore we get Sam printed on the console. Similarly, we will get Gary also on the console. But notice the last two clauses will not succeed, because even though this half succeeds, the second half will not succeed because the comparison fails. So this will be abandoned, and so will this, and there's no more solution. So the while loop terminates, because the relation the fourth time around will return false and fall back out of the loop. So that's the basic mechanics of backtracking. One little example that I might want to point out here is, notice how the paradigms are blending. We are phrasing the question and performing the computation in the declarative domain and performing I/O in the imperative domain. And also notice how lightweight syntax we are using here. If I am interested in performing I/O in the declarative domain also, this is one way to do it. I would say write the value of P and write a space and get rid of this part here and put a semicolon there. Now I basically moved this into this. I'm performing the computation and the I/O in the declarative domain. Let's see if it gives us the same answer as before. So you see Frank, Sam, and Gary being printed. So the idea is that you can switch between paradigms depending on what you're doing. I personally prefer to do I/O typically in the imperative model, because I/O by nature is an imperative task. However, there are many cases when I/O is essential to be performed in the declarative mode, and we have support for that in Castor. So let's put that back here. Now similarly, if we can generate all P and G pairs, and how would we do that? By simply leaving both arguments unspecified. I am going to print the value of G also, and let it run. Okay, looks like I forgot to remove this semicolon here. So let me run that again. So we have all the pairs of people and gender. Now again, the basic idea is that both halves would perform assignments as opposed to comparison. I should perhaps mention here that at the end of the execution of this while loop, once I have exhausted all the solutions generated by that relation, the values of the logic references P and G are going to be reset to their original values, which is undefined. So at this point, if I were to try to print P and G, this would lead to an exception because it's an undefined value. It's like uninitialized pointers basically at this point. So now I'm going to continue building on this example, but before I do that, maybe I'll just put this example into context. You can think of this as the hello world of the logic paradigm. Our interest here is not to be solving some particularly interesting problem, but to get a hang of the fundamental dynamics of the paradigm. So once we have that foundation, we can apply those principles to solve some interesting problems. So now I'm going to add a few more relations to make this a little more interesting. The first relation I have here is the child relation. We are basically stating child relationships. So we are saying C is a child of P. There are 4 children, or actually 1, 2, 3, 4. There are 5 children I've mentioned here. So we are stating that Sam is child of Mary, Denise is child of Mary, Sam is child of Frank, and so forth. So now that we have the gender and the child relation, we can infer some more information out of those. For instance, we have the father relation. We are saying F is a father of C if F is male and C is child of F. Similarly, we have the mother relation. Here we are stating that M is mother of C if M's gender is female and C is child of M. So it's very similar to the father relation, only differences in the gender. Next, we have the parent relation. We state that P is a parent of C if P is a father of C or mother of C. We can also state it more concisely as follows using the child relation simply by flipping the order of the arguments. So if C is child of P, then P is parent of C. The real relation I'm trying to get to here is the ancestor relation. The goal here is to demonstrate recursion. A parent-child relationship is a direct relationship, whereas an ancestor relationship, there could be multiple levels in between an ancestor and a descendant. So therefore, in order to step through the family tree, we are using recursion. Here our base case is a parent is also considered as an ancestor of a person. So if you are a parent of some person, you are also his ancestor. So let's read this out. We are saying that A is an ancestor of D if A is parent of D or A is a parent of some X. X is not defined yet, the value. So A is a parent of some X and the person X is an ancestor of D. This will basically generate a value for X and here we will consume it. We are stepping down the family hierarchy tree. We are generating a child of A and then testing if that child happens to be a ancestor of D. So this is the recursive step. Although the specification is theoretically correct, there's a small implementation issue here and we'll examine what that is. Now I'm going to try to ask the question, who are the ancestors of Sam? So what I'm doing here is asking that question, ancestors of Sam, by passing the first argument as the ancestor A and the descendant would be Sam, and A is an undefined logic reference. and then I'm going to loop through all solutions and print the values of A. Now the problem with here at the moment is that there is infinite recursion, and let's examine how that happens. What happens when we invoke the ancestor relation? At this point, C++ will execute this expression, and when that occurs, we have a recursive call immediately to the ancestor relation itself. And when that is evaluated, we go back into the same expression and keep going on in that cycle. So what's happening here is the recursive step is taking place at this point and not at this point. This is example of eager recursion, what we are normally used to. What we want is delayed recursion. So we want the recursive step to be executed only when we actually look for the results. So what we're going to do is convert the eager recursion into lazy recursion, and we do that using the ancestor the recurse relation. This is simply an adapter relation which we can use to turn eager recursion into delayed recursion. So now if we build and run this example, we should see all values of A. So we see Frank, Mary, and Gary. All right. Let's recap on what we have learned in this demonstration. The first thing we saw was unification. Unification is basically a combination of assignment and comparison. We also saw backtracking. Backtracking is basically going and looking for alternative solutions and not starting all over again. We keep exhausting all our alternatives, and finally once we are done, there's no more solutions to look for. That's the second thing. Third, we saw bidirectional use of arguments. So when we leave an argument's value unspecified or undefined, that argument behaves as an out parameter, whereas if you specify a value for an argument, it behaves as an in parameter. So relations can be used either to test if a condition is true, which you do by specifying values for all its arguments, or you can use the relations to generate values instead of just testing them by leaving their arguments undefined. And this ability to treat arguments as bidirectional arguments is a source of a lot of expressive power that we get from the logic paradigm. The other things to note is how the paradigm blends with the imperative paradigm. Notice how you are able to switch back and forth. If you recall from the IO example, that we could decide to switch IO into the declarative domain if we wish to, instead of the imperative model. So in a sense, you have fine-grained choices that you can make of where to do certain computations. The other thing to note is how we're using an imperative, a simple imperative looping construct like the while loop and the if statement to go over the solutions produced by a relation. Once again, the syntactic overhead is minimal, and it blends quite naturally into the imperative paradigm. The other aspect of this integration of paradigms is perhaps slightly more subtle, and that is the overall syntax that we have been using to define the relations. We have defined the relations simply as functions. We did not have to implement them as a class which derives from another base class provided by the library, or have to define certain member functions and so forth, or virtual base classes, or any of that complexity. None of it is required. Neither did you have to define them as template classes with other template trickery. Our syntax is very simple and straightforward. This is one way to represent relations. You could also, if you wish to, represent them as classes. You could do that. That's something I'm not covering in this demo. The key thing to take away from this example is the fundamentals behind the logic paradigm, which is unification and backtracking and recursion, and the overall mechanism, the syntactic approach, which actually blends very naturally into the imperative paradigm. A big benefit of this overall approach is that it allows us to use our existing design patterns and apply them to the logic paradigm. For instance, since you can define these relations as simple functions, you can also define them as member functions or static member functions, or derive relations from base classes, or make them virtual or pure virtual, and so forth. So you can see how it blends into the object-oriented paradigm and allows us to bring in the design patterns from that space and extend them over to this multi-paradigm space. Similarly, you can also implement these as template functions or member template functions, and that sort of blends into the generic paradigm also. This ability to mix and match and blend the paradigms cleanly at a low level is very crucial to multi-paradigm programming. Coming back to the slides, let's briefly go over the fundamental primitives that we've used to program in logic. As you can see from the slide, there are actually very few primitives that are truly required to support the logic paradigm in C++. Let's go over each of them briefly. The first primitive is the logic reference type. Conceptually, it is similar to references in C++, but the key difference being that logic references do not need to be initialized. We can check if the logic reference is currently initialized using the defined method. We can also use the star and the arrow operators on the logic references to access the underlying value. The logic references are basically implemented as smart pointers. If we dereference a logic reference which has not been initialized with a value, it throws an exception called invalid deref. There are three semantics of interest in the context of logic references. The first one is initialization, the second one is assignment, and the third is copy construction. So here we have initialization. It's very simple. You just initialize it along with the definition of the object, the logic reference, and what it does is at this point makes a copy of the value supplied to it and keeps it internally. Now, since the li1 over here, which is a logic reference to an integer, has been initialized, if we invoke defined on it, it returns true, whereas invoking defined on li2 returns false because we have not supplied a value to it yet. Once we have supplied a value to it by assignment here, the defined will return true. Next is the assignment semantics. Assignment basically makes a copy of whatever is assigned to the logic reference. So for instance, here we have two logic references to strings, ls1 and ls2. ls2 is being assigned ls1, which basically means the value leader is going to be copied into ls2. Similarly, when we assign s to ls2, the string Castor is going to be copied into ls2. So assignment, that's all there is to it. It basically implies that we are performing a copy of the right hand side. Copy construction is interesting because unlike assignment, it does not create a copy. So when we copy construct a logic reference from another one, we are basically creating co-references, meaning that both logic references point to the same underlying object. So they are bound to the same underlying object. For instance, here we are initializing ls3 with ls1 copy construction. Once ls3 is copy constructed, we assign the value logic. Now, since both references refer to the same underlying object, changing the value of 1 will make the same change visible in the other logic reference. So even when we print the value of ls1, we'll actually get the new value. The next example here shows two logic references, so li1 and li2. li2 is being copy constructed from li1, and in this case li1 is not initialized. So at this point li1 and li2 are both not initialized, but as soon as we assign a value to either one of the logic references, both logic references will see the same value. So here li2 will also print the value 4. Coming to the unification relation. Now this is conceptually quite simple relation. It is basically a combination of assignment and equality. Its arguments are either logic references or regular values. If the logic references are initialized, in that case unification will perform comparison. So the result of the unification is the same as the result of the comparison. If the comparison succeeds, so does unification, otherwise it fails. The other condition is that one of the two logic reference arguments to unification is not initialized. In this case, the value of the initialized argument is assigned to the one which is not initialized. This basically makes both arguments equal, so it returns true. The last case is when neither of the arguments are initialized, neither of the logic references are initialized. In that case, unification always fails by throwing an exception. So this is basically an error condition, and the name of the exception is invalid deref. It's basically trying to dereference one of the arguments, and that attempt fails. The type relation. Now this type is actually the key ingredient which allows a simple syntax in C++ for programming in logic. All it is a type to which arbitrary function objects can be assigned. For instance, we have a simple function object being defined here. So the function object that we are interested in assigning to a relation needs to satisfy one fundamental requirement, and that is it should not take any arguments and return type bool. Now, as long as we have a function object which satisfies this requirement, we can simply assign it to a relation. So for instance, we are assigning f to r. Once we have assigned f to r, the original type of f is no longer accessible. However, when we invoke the function call operator on r, it will trigger the evaluation of the function object itself that was assigned to it. So in a sense, it's simply a placeholder for storing function objects. This idea of a relation is very similar to the boost function as defined here. The key difference between boost function and the type relation is that you cannot assign global functions or member functions or static member functions to type relation. Only function objects are allowed. Finally, coming to the operators. Now these three operators, the AND, OR and exclusive OR, these are the three operators which provide the backbone for the backtracking subsystem. We know that these three are all binary operators, but an interesting aspect of the implementation of these operators is that they are all implemented as relations. Not only are they relations, but they take other relations as arguments. So basically they are relations which take other relations as arguments, and that makes them higher order relations. Any relation which takes another relation as argument is referred to as a higher order relation. Since these operators are themselves relations, they can potentially succeed multiple times. And exactly how many times they will succeed depends upon what arguments are passed to them. So remember, their arguments are relations which can potentially also succeed more than once. And depending upon the semantics of the operator in question and the specific usage of it, it can succeed 0, once, or multiple times. It is not necessary to understand the detailed implementation of these operators, especially in an introductory talk, in order to start using the logic paradigm. So I will not be covering them in detail here, but suffice to know that the implementation is very lightweight on these operators. Together, the implementation is a sum total of 100 lines of code for all of these three operators. I'll cover the basic semantics of these operators here and leave out the details regarding their implementation and exactly how they work for a separate presentation. These details are described in a document that's available on mpprogramming.com. This document basically talks about the design and implementation of the Castor library. If the descriptions that I'm going to provide now are not totally clear, do not lose heart, because a basic understanding of these operators is sufficient, and with use their exact semantics become more clearer. This may be a little bit confusing at first, however it's not that complicated, and with experience it becomes quite natural to develop an understanding of exactly what happens behind them. The AND operator basically succeeds whenever both its arguments succeed. The way it goes about evaluating both its arguments is, the first time we evaluate the AND operator, it evaluates the first argument. Now if the first argument succeeds, then it goes on to evaluating the second argument. Whereas if the first argument does not succeed, then the OR operator has no more solutions to produce, and therefore it returns false immediately. So let's consider the case when the first argument did succeed and it went ahead and evaluated the second argument. Now assuming the second argument also succeeded, this is a condition where the AND operator succeeds, because the first argument and the second argument have both succeeded. So the AND operator returns true back to the caller. Now when the AND operator is evaluated the next time around, it will directly evaluate the second argument, and the third time around it will again evaluate the second argument. This continues as long as the second argument keeps succeeding. Now once the second argument stops succeeding, it goes back and evaluates the first argument. Now if that succeeds, then it repeats evaluating the second argument all over again until the second argument fails. You can think of this, a simple description for its behavior as, it produces all solutions from the second relation for each solution in the first relation. The OR operator, on the other hand, goes through all solutions in its first argument, and then it switches over to the second argument and goes over all its solutions one at a time. Each time the first relation or the second relation succeeds, it is a successful evaluation of the OR operator itself. Now the exclusive OR operator This can be thought of as something analogous to the if then else statement that we have in our languages, in a sense that the second argument will not be evaluated ever if the first argument succeeded. And vice versa, if the first argument never succeeded, then the second argument should succeed. Otherwise, the entire exclusive OR operator is considered a failure. You can think of it as generating solutions from the second relation only if its first relation never produces any solutions. And if the first relation does produce any solutions, it keeps looping over those solutions till they're exhausted. One thing to keep in mind when using the exclusive OR operator along with the other operators in the same expression is that it has higher precedence than the OR and AND operators. So you might have to use extra brackets to make sure the right arguments are passed to the exclusive OR operator. Now coming back to code, our examples so far have been more Hello World style examples where our motivation was to primarily get an understanding of the fundamental concepts behind the paradigm. In these examples, we'll actually apply those concepts to some slightly more interesting problems, so we develop a better feel for the paradigm as to how it's actually used in practice. In this first example, I'll start by looking at a function that's implemented imperatively and then define the same declaratively. We have the get matching numbers function here, which takes 3 arguments. The first two define a range, min through max, that's an inclusive range, and a predicate function, which will be applied to all values in this range, and the result will be all the numbers that match the range, match the predicate. We have the for loop which basically goes through the range, then the predicate is applied to the number generated. If the predicate succeeds, we add it to the result and finally return the result. I have the is-even function here, which is a simple predicate function, which I will use as argument to generate all numbers 1 through 10 which are even. Then we iterate through the result from beginning to end and print the values in the list. Now let us implement this same thing declaratively. I will need a logic reference for this. So I'll define the even numbers relation as follows. So what I'm saying here is j is a number in the range 1 through 10 and satisfies the predicate is even with the argument j. And now I will trigger the evaluation of the relation and print the values of j. So here I am generating values from 1 through 10 for j, and here I am testing the values of j using the is even predicate. The relation predicate is an adapter relation which allows us to treat existing predicate functions, meaning functions which return bool, as relations. So you can take a predicate function and using the predicate relation we can treat them as relations. Now let's run this code and make sure that we get the same results imperatively and declaratively. So we can see here that both the imperatively and declaratively they produce the same result. Let's move on to examining this little function is even and see if we can actually further simplify this code. So this function is even. The only purpose is to encapsulate this little expression which computes if a given number is even. And for that purpose, we have to create a function, name it, pass it an argument, return type, and a return statement, and then pass it to the predicate relation. Instead, we could use lambda expressions as follows. We directly specify that arithmetic expression inline. This inline expression is referred to as IL, inline logic reference expression. This IL is just a lambda expression. What happens here is, since this arithmetic expression consists of at least one logic reference, it is not evaluated immediately. Instead, this expression will be turned into a function object and passed to whatever relation we are working with. In this case, the predicate relation. So we are basically passing an anonymous function to this predicate relation. So the behavior should be the same. Let's make sure by running this code. We see that the same values are printed again. So let us try to understand how we were able to express all of this functionality just with this little expression here. There are a couple of reasons for that, other than the fact that we've used lambdas. First, we've seen that relations have bidirectional arguments, which basically allows simple relations like range to be used in many different ways. So from that we get a lot of power. And the other one, the second reason, is a little more interesting and subtle. And for that, let's understand and analyze the concept of a for loop. Notice the for loop here in this function. Like any other for loop, it has a header and a body. In all our languages, we have this concept of a loop with a header and a body. But the key issue with these loops is that the header and the body are tightly coupled. You cannot decouple them very easily. In this function, there's already an attempt to decouple the body by trying to parameterize what happens inside of it by passing the predicate function and using that in the body. However, this technique doesn't scale very well, especially when you have multi-level nested loops or there's a lot of data sharing between the body and the multiple levels of nested loops. If you also look at the standard algorithms in the C++ library, you will see that they are actually attempts at giving you prepackaged loops like the copy or the transform, where you can perform certain amount of parameterization. Here, let's try to observe their correspondence with the for loop. Now the header of the for loop is actually doing the same task as the range relation here. They're both actually generating values in the range. And the predicate relation here is doing what the body is doing. It's consuming the value. Now the range relation and the predicate relation here have been implemented completely independent of each other and have no clue even in this expression as to how they're interacting with each other. So range has no idea how the value of j is going to be consumed, if at all, and the predicate relation has no idea as to where the values for j actually come from. This decoupling of relations allows us to actually write very simple relations and combine them in arbitrary ways and quickly build a lot of functionality out of very little code. So this is actually an important observation. Now let us try to understand the performance of this declarative code. We certainly know that this code is more concise than the imperative implementation, but how does it compare in terms of performance? It might be surprising that this code actually runs potentially 100 times or more faster than the imperative code. The exact number is less important, but what is more important is how does this actually perform better than the imperative code. To understand that, let's take a look at the getMatchingNumbers function. The getMatchingNumbers function returns a linked list and it keeps adding a value one at a time into the list. It does this because it does not have a clue as to exactly how many numbers are there in the collection, so therefore it uses a list and keeps adding values into the list as the values are discovered. Memory allocation is what happens when you add a node into a linked list. And dynamic memory allocation is expensive, especially if you are in a multi-threaded program. So even if this piece of code is not multi-threaded, but your overall application has been compiled with the multi-threaded flag turned on, this piece of code is going to pay the penalty. Now, if you're talking about large lists, so for instance, if this range is talking about from 1 through 1 million, then your result is going to have 500,000 elements in the linked list, which means 500,000 allocations, and that is quite expensive. Whereas in the declarative code, each and every value of j is being produced in the same memory location. It is then consumed and the new value of j is overwritten into the previous memory. So basically we are discarding values as we have consumed it and keep reusing the same amount of memory or the same memory location. So this basically means we have cut down the amount of memory required for this computation, and also we have cut out the number of memory allocations required for this computation. This is the reason for the performance improvement. Let's move on to the next example. Now this example deals with Pythagoras triplets. I'll just paste some code directly so you don't have to watch me type it all. I have logic references x, y, and z which will represent the triplet. Max is 30. What I'm actually interested is all Pythagoras triplets where the value in the triplet is less than 30. So the relation is defined as x is a value in the range 1 through max, same with y and z. So x, y, and z all are in the range 1 through max, and they need to satisfy two predicates. X square plus y square is z square, or z square plus y square is x square. Now the only difference between these two expressions is the position of z. Here it is on the right hand side, here it is on the left hand side. So this basically allows me to generate all the combinations like 3 4 5, 5 4 3, 5 3 4. Let's just run this code. Notice here we are actually evaluating the relation and printing out the values of the triplets. Let's see what output we get. So we have the triplets being generated. Our basic triplets are 3 4 5 4 3 5 and so forth. If you are interested, let's say for instance, to generate all triplets where x is 15, all we have to do is initialize x with 15 and run the code. So this basically gives us all triplets where x is 15. Similarly, we can initialize other numbers. So if you want to find all triplets where y is 4, so we have two triplets. So in a sense, we can keep playing around with this, initializing different logic references with different values and checking if a certain triplet of a certain nature exists and so forth. So this is again a demonstration of the bidirectional nature of the arguments to relations and also inline logic reference expressions or lambda expressions. Now moving on to the next example, once again I will paste the code. In this example, we look at how we can mix the STL with the logic paradigm. I have a vector here, Vi is initialized with the elements in this array. And now I'm simply going to iterate over all the elements in the vector and print them out one by one. So the relation here is to be read as follows. I is an item in the sequence bounded by vi.begin till vi.end. And then we evaluate the relation and print all the solutions which are generated in I. So let me print the values here by running the code. So as you can see, the values 0, 1, 2 and 3 are printed. We can also use pointers instead of iterators directly. So for instance, I could print the elements in the array AI. So this time my sequence is AI, the 0th element, all the way to 1 past the last element. So once again we see the values in the array being printed. So this is basic iteration. We can work either with pointers or with iterators. Now let's make it a little bit more interesting. Since we can perform iteration, which is sort of the most basic operation we can perform over sequences, now we can use that to perform some more interesting computations. So here I'm trying to find the intersection of two arrays. So I have array 1 and array 2 here, and my goal is to find out the intersection of the two arrays. So I have two logic references I and j. I will iterate over the first array and j will iterate over the second array. So what I'm saying here is I is an item in the first array and j is an item in the second array, and I should be equal to j. So we want all the common elements in the two arrays. So let me run this code and see what values it prints. It prints 1 and 3. So notice those are the only common elements in the first and the second array. We can actually simplify this a little further by getting rid of j and also getting rid of the predicate here and replacing j with I. So what we are stating here is I is an item in the first array and I is an item in the second array. So this will produce all values of I that is in the first array, and this will test those values in the second array. So let's print that out and we should see the same result again. 1 and 3. So this is intersection, which naturally brings us to performing union. We would compute the union simply by saying I is an item in the first array or in the second array. So now let's see the new result for the union. We see the items in the first array, then the items in the second array. If you notice the results, let me run that again. If you notice, the union had duplicate elements. So for instance, 1 is repeated twice. That's because 1 occurs in both the first and the second array. So if we were interested in actually filtering out duplicates, we could put a bracket around this expression and say that I should be unique mean. So unique is a relation which we're using to filtering out duplicates here. So we see the duplicates have been filtered out. So this part of the expression generates values of I, which basically represent the union, and this part of the expression will filter out the values of I if they have been seen in the past. We could also do additional filtering. For instance, look for all positive numbers only. So this is going to give you all unique positive numbers in the union of the two arrays. Essentially, this expression is a query expression. We are issuing a query declaratively over the two arrays. For this next example, I'll briefly switch over to the slides because it's easier to see this example in the picture first. I have a directed acyclic graph here with about 5 edges and a relation edge which describes the edges in the graph. So the way we would read this relation is as follows. There exists an edge from n1 to n2 in the graph if n1 is 1 and n2 is 2, or n1 is 2 and n2 is 3, and so forth. So we have one clause for each edge in the graph. Next, we can define what a path means using the definition of an edge. So here we are stating there exists a path from start to a node end if there exists a edge from start to end, or there exists an edge from start to some node x and there exists a path from that node x to end. This is the recursive step, and the overall definition is very naturally recursive. Now let's actually see the path relation being used for the different kinds of computation it supports. Now I have the same relations edge and path that we saw on the slide, and here I'm using the path relation to check if there is a path which begins at 1 and ends at 4. So if the evaluation succeeds, I print connected, otherwise not connected. From the first 3 clauses we can see there's a edge starting at 1 ending at 2, another one from 2 to 3 and 3 to 4, which implies that 1 is connected to 4. So if I run this, we should see connected printed out on the console. We could also flip the arguments and check if 4 is connected to 1. And if you look at the clauses defining the graph, you will notice that there is actually no edge which begins at 4. So we need to see not connected printed on the console. We could also use this relation to generate all the nodes which are reachable from a particular node. So let's say we are interested in finding out all the nodes that are reachable from 5. So here we would print the value of x and use a while loop to iterate over all solutions. It says 4, 2, 3 and 4. So let's cross check the solution against the picture of the graph. So we can see there is an edge from 5 to 4. That's the first result. Another one from 5 to 2. And then there's a path from 5 to 3 via 2. And another path from 5 to 4 via 2 and 3. So basically there are two paths from 5 to 4. One is this one, and the one is the direct edge between 5 and 4. So that's why we see 4 being printed out twice. In this example, all the vertices and edges of the graph were known at compile time. However, there may be cases when this data is available only at runtime. In such cases, we have to be able to define our relation dynamically. For this, Castor provides 3 types: conjunctions, disjunctions, and exclusive disjunctions. These 3 basically correspond to the operators AND, OR, and exclusive OR, and together they give you the ability to define any relation dynamically that can be defined statically. The important thing to observe is that these 3 types are themselves relations, so they can be used wherever a relation is required. Now let's see how the edge relation can be implemented using the disjunctions relation. Let's assume that the edges in the graph have been read into this vector of pairs from a file, and each pair is basically an edge. In this for loop here, we are basically iterating over the vector, picking up one edge at a time and adding that edge into our list of clauses, which is a disjunctions relation. So this expression is itself a relation which is being added to our list of clauses. And finally, once we are done iterating through the entire vector, we return the list of clauses, which is a relation. Coming to the final example. Now, if you recall the examples that we've seen so far, we initially started off with examples more like the Hello World style examples, where our motivation was to see how the fundamental concepts are represented in code and see them in action, things like unification and backtracking. Next set of examples involved around applying those concepts to solve some simple but real problems and get a better feel for how the paradigm is used in practice. In this final example, we are going to step one level higher and observe the impact of multi-paradigm programming on overall software design and implementation. For this, what I'll be doing is contrasting 2 implementations for the same software. One is a uniparadigm approach, which uses only the object-oriented paradigm. The other one is a multi-paradigm approach, which also uses the logic paradigm. What I have here is a game of chess. And if you're not familiar with the game of chess, that's okay, because you can think of this as some arbitrary board game, which, like all other board games, has a board and a set of pieces on it, and then there are some rules which govern how the pieces move on the board. When you start thinking about this game in an object-oriented fashion, you will see it's quite natural to decompose some of the elements on the screen. You have the board, which you could represent as a class. The board is a collection of cells, and the cells you could represent them as a class. You have different kinds of pieces, and each kind of piece you could represent as a class. And we could potentially have a base class for all the piece types that we have on the board. Each piece knows, for instance, where it belongs on the board, meaning on which cell it is located, its own color, and also the kinds of moves that it is allowed to make as determined by the rules of the game. So for instance, when I move this piece from its current location to this new location here, what I'm doing is invoking a method called valid move on that piece. The arguments to the valid move method are is the new position of the piece. When I invoke this valid move method, the piece looks around the board and determines whether the move to the new position is actually valid. And if it is valid, it returns true, otherwise it returns false. And this is the basic approach taken in both implementations of the game. Most of the rules of the game have been distributed into the different pieces that we have on the board. And each time we move a piece to a new location, we invoke the valid move method on it. If it returns true, we move the piece from its current location to the new location, otherwise we leave it at its current position. One thing to note about both implementations of the game is that neither of them support a computer playing against a human. There's only support for two human players playing against each other. This does not have the intelligence to determine which move among the possible moves is the best and then make that move. It only enforces the rules of the game as two human players make their moves. And we'll be examining most of the implementation in terms of this piece here, which is called the rook. The rook is allowed to move either vertically up and down or sideways, left and right. So now let's take a look at the code. We are looking at the object-oriented implementation of the program. This is the header file which contains the class declarations for the different abstractions we identified earlier. The structure pane to the left gives us a summary of all the types that are found on this file. So we can see the piece class, which is the base class for the different piece types that we have, like the pawn, the rook, and so forth. Then we have the cell class, which represents an individual cell on the board, and the board class itself, which is the collection of all the cells. Here's our rook class and the valid move method. This method is declared to be pure virtual in the base class and defined in the derived types. It takes the new position as argument and returns true or false. Switching to the implementation of this method, if you recall, I mentioned that the rook moves only vertically or horizontally. So it moves either up and down or sideways. And if it's neither a vertical move nor a horizontal move, then it's an invalid move. So that's what we're going to check for. We're going to check first to see if the current position and the new position have the same rank. Rank is chess terminology for row. So if the new position and the current position are on the same row, then it's a horizontal move. Else, we check if the current position and the new position share the same column. File is chess terminology for column. And if they do, then it's a vertical move. If it's neither horizontal nor vertical, then we return false. Now let's look what happens if it's a horizontal move. First, we quickly identify if it's a horizontal move to the left or to the right. And once we do that, we simply loop over all the cells between the current position and the new position, either left or to the right, and make sure that the cells between the new position and the final position are clear. So this is the basic idea of how we go about implementing the basic logic behind most of the pieces. They examine the board to understand what the current situation is and if the move is valid. Now let's take a look at the multi-paradigm solution for the same program. So we'll begin by taking a look at the header file. Again, this header file contains all the class declarations for the different abstractions, and the structure pane shows us, once I collapse it, that we still have the same basic abstractions, the piece, the rook, pawn, and so forth, the cell, and the board. So the overall abstractions have stayed the same. What has actually changed is the implementation of the valid move method. Here's our rook class. Here's the valid move member function that we saw earlier. We have added a relation. This is a member relation, also called valid move, and it takes the rank and the file explicitly split out. Now let's take a look at the implementation of these two. So here's our valid move member function. This time we have implemented it in terms of the valid move relation. We first invoke the relation and then trigger the evaluation on it immediately. So here we are using the valid move relation to check if a move is valid. Coming to the valid move relation, here just like before, we first check if it's a horizontal move, a valid horizontal move, by ensuring that the new rank and the current rank are equal, or it's a vertical move by checking the current column and the new column. If it's a valid horizontal move, then it's a valid move to the left or a valid move to the right. In the case of the vertical move, it should be a valid move up or a valid move down. These four relations, their job is essentially to make sure that the path is clear between the current position and the new position. Now, what did we gain by implementing this relation? Our function, the member function valid move, could only check if we can move to a new location, whereas this relation can not only check, it will also generate all valid locations to which a rook can be moved to. In addition, we could fix one of the two arguments like the rank or the file and generate all the valid vertical moves only or only the horizontal moves. Now this ability to generate the different moves is a huge leap in functionality for the game programmer, because simply checking if a move is valid is a much simpler problem than generating all valid moves. Now that you can generate all the valid moves for a given piece, you can also do that for any piece on the board, which means the game programmer can easily identify all possible moves for all pieces on the board. Now all that is left so that the computer has enough intelligence to play against a human is to build some intelligence which evaluates all the moves and assigns them a priority, so we can say which move is the best of all the possible ones. Now the real motivation behind this example was to understand the impact of multi-paradigm programming on the design and implementation of software. So first let's consider its impact on design. In this solution, we represented the different pieces on the board itself and the cells as classes, because the object-oriented paradigm is the most natural paradigm in order for us to represent these concepts with. But the rules, we implemented them as relations, because rules are by nature declarative and so is the logic paradigm. So in summary, we represented objects using the object-oriented paradigm, but the rules of the game with the logic paradigm. Now let's understand the impact on the implementation. We saw that we gained a significant functionality increase by representing the rules as relations, because now we are not only able to check if a move is valid, we can also generate all the valid moves. What about the size of the code? Now this is the multi-paradigm solution. Let's take a look at how many lines of code were involved in this solution. So I'm going to the bottom of the file, and here we have about 675 lines of code. So this is the multi-paradigm solution. and the pure object-oriented solution was about 1100 lines of code. So we can see that there was about a 40 to 50% reduction in the size of code. There was an increase in the functionality. Now, if we were to say that generating all valid moves is about twice as difficult as simply checking for a valid move, then you could say we doubled our functionality by cutting our implementation by about half. That summarizes the impact of multi-paradigm programming on design and implementation of software. There are other areas where multi-paradigm programming has an impact, things like performance, readability, debuggability, and so forth. Since this is an introductory talk, we will not cover all those different aspects. That concludes our final example. And before I wrap up, here's some brief overview regarding the Castor library that we have used to program with the logic paradigm in C++. It's a freely downloadable open source library. You can get it from mpprogramming.com. It's distributed under the MIT license. The library has been entirely implemented in header, so it's a pure header library and there's nothing to link with. There's a list of compilers mentioned here against which the library has been tested. This covers the various Windows, Unix, and Mac platforms. There's more information available surrounding the paradigm and the Castor library. The first document mentioned here is an introductory tutorial which covers the basics of the paradigm, how to use it in C++ with some examples and so forth. The next is the reference manual for the library. Skimming through the table of contents of this is a quick and easy way to get a glimpse of what facilities are provided by the library. The last document here talks about the design and implementation of the core portion of the Castor library. This core portion is what enables the logic paradigm in C++, and all the other facilities are built on top of this core. And all these three documents are part of the download of the library itself. So with that, we have come to the end of this presentation. I hope you have enjoyed this, and thank you very much.